Welcome to CHUKS Physics and Maths classes. In today's physics class, we will look at elasticity theory, which simply means I want to believe that you must have followed my classes on elasticity 1 and 2. In the first case, we considered the meaning concept of elasticity and its applications in the field of engineering and technology and other sciences. We also studied the inelastic materials, and in the second one we considered the empirical formula for calculating the elastic properties of materials, otherwise known as the Hooke's law of elasticity. And in this case, we are going to discuss about moduli of elasticity. Moduli of elasticity. By moduli of elasticity, we are talking about the overall response of materials to either stretching or compressive stresses. Moduli of elasticity deals with ratios, terms or factors that describe the overall deformation or distortion that occurs in a body under the influence of a tensile stress. That's the strength produced. Alright. Having known that, of course, we know that the Hooke's law describes only unidirectional deformation or strain on a body, while in real life situations, materials undergo 2 to 3 dimensional deformations under compressive stresses and stretching. And also fluids, which are dimensionless substances, can also be described in terms of these 3 dimensions of deformation. Thus, the first of a moduli of elasticity we will consider is the Young's modulus. Young's modulus of elasticity. Young's modulus of elasticity. There are 4 moduli of elasticity I'll bring to your notice. They are Young's modulus, Poisson modulus, and shear modulus, and then of course bulk modulus. We start with this one, Young's modulus. The Young's modulus discusses the strain, the ratio of the extension to length produced in a body by a compressive or stretching stress. Thus, if a body of initial length L0 and area of cross section A is being stretched or compressed by a force F, then the tensile stress produced, the tensile stress applied, is equal to force over area. That's the tensile stress is force per unit area, and it is otherwise known as pressure. The stress applied to a material either to stretch it or to compress it. Of course, like rods used in buildings are under compressive stresses. So the force, the pressure there can be stretching or compressing. And the pressure or stress is given by force over area in the unit of Newton per meter squared. Then the strain, tensile tensile strain produced in the same material as a result of this stress. The deformation, distortion, or damage produced in the material when it is being stretched is given by change in length over original length. And that is E over L, original length. And in an analogous statement to Hooke's law, we discover that stress is directly proportional to strain. And therefore, mathematically, that becomes stress equal to Y times strain. This Y is a constant of proportionality called the Young's modulus, and it is given by stress divided by strain. So Young's modulus is defined as the ratio of stress to strain. The Young modulus is stress divided by strain. And of course, we know that stress is F over A, while strain is E over L. Therefore, Young modulus can be expressed as FL divided by AA. This is the relation for the Young's modulus. Take note of it to calculate Young's modulus or any of these parameters. FL over AA. F is the force, L is the original length, A is the area of cross section of the body, E is the extension produced. And the Young's modulus has a unit of, yes, the Young's modulus has a unit of Newton per meter squared. It is a scalar quantity. Okay. Having known this, materials have their Young modulus. Found in the statistics of physics. We head straight to the second one, known as Poisson modeling. Poisson ratio or moduli. When a material is being stretched, common experience shows that its deformation occurs in both length and width directions. And this is summarized by the Poisson moduli of elasticity. Assuming we have a material of this nature, we have a material like a rod of this nature, and a force, a tensile stress is applied here, a force to pull it, drag it upward. Then the original length L0 will increase to this point, to a new length, which is L. And this increment is E. This is E. And the E is equal to change in length, which is L minus L0. Then it is also noticed that when a body is being dragged, the cross-sectional area, the diameter reduces from D0 to, say, a point here, which is the final D. And the change in length, we now summarize this as follows. The change in length is equal to L minus L0. That's the change in length. And therefore, fractional change in length is given like this. And that is, this is the fractional change in length. All right, that's the deformation produced towards the length axis. Correspondingly, the width reduces from D0 to what? To D. and that is change in width. Thus, the fractional change in width is given by this, and that is negative. Since D0 is greater than D. And in an analogous way to Hooke's law, we discover that the fractional change in width is directly proportional. That is directly proportional to the change in length, and that is ED is equal to. Therefore, sigma is equal to EL over ED, where this sigma is a constant of proportionality called Poisson's ratio. This is the Poisson's ratio. Take note of that. So the Poisson's ratio is a ratio of fractional change in length to fractional change in width of a material. And finally, we discuss about the shear modulus. Shear modulus of elasticity. Before we continue with this, take note of these two. And let's pause this for the next class. Take note of this.